Hello, welcome to Chapter 7 Dimensional Analysis, Similitude and Modeling. We are going to finish this chapter in this video. So, last time we have seen this example. We have this thin rectangular tube and we want to develop suitable set of pi terms for the drag force on this plate. So, what's happening in this plate is inside your fluid, inside water, and as water flows, this drag force is formed, and that drag force is a function of these 5 variables, and we want to find out what is the pi terms for these drag force or for pi terms for these problems, combination of these 6 variables. So we start with Buckingham pi analysis. We start with step 1, list all the variables. Step 2, get your k terms and r terms, write down basic dimensions. Step 3, your k terms and r terms are nothing but 3, so you are going to have pi 1, pi 2, pi 3. Step 4, choose variables. In this case, we are not going to choose drag force, we are not going to choose, let's say, height, we are going to choose width, we are going to choose density, we are going to choose velocity. We choose that, we avoid viscosity because it has complex unit. Then we do our process, we write down in this form, and then you get the values of a, b and c, and then you try to make it dimensionless. So you find out, and then you will get first pi term like this. Then next part, you take the variable from h, you put it in here, and then write down, get your pi terms, pi 2, second pi term like this, get your values of a, b, c, get the pi 2, and then for the third part, pi 3, you take viscosity, plug that in here, and calculate pi 3. That's what you can do here. So once you have that pi 1, pi 2, pi 3, you write them down like this, and then you have your final answer. Pi 1 is function of pi 2 and pi 3. Now why did we do that? Why we use this? What is the purpose of this dimensionless parameter? Remember, my objective here is to help this dimensionless parameter to perform an experiment. Let's assume that this plate is extremely big, it's very big, and I want to know drag force on this plate in the air. Now, as this plate is very big, I don't have that big of a wind tunnel. I cannot do my experiments on this plate. So, what I do next best thing. I build a small model of this plate and I test it in wind tunnel or in water tunnel, and then I try to scale up my results to understand drag force for the plate. I try to predict my results on this big plate. It means that I will try to understand how this big plate will behave by doing the experiment on small plate, and that's when these parameters come into picture. So now our objective is to designing a model that could be used to predict the drag on certain full-scale prototypes. So this one is my full-scale prototype, this one is my small plate. I want to know drag force on full scale by experimenting it on small scale. That's the idea. Now the way to do that is, this one is my pi term that I got with Buckingham pi theorem, pi 1, pi 2 and pi 3. The way it works is that for this full scale type and for the model, these parameters are going to stay same. It means this one is for full scale prototype, and when I write m suffix, this one is for model. So I can say that this ratio, this term, I have another Wm by Hm, that the dimensions for the model has the same ratio for dimension of a prototype. Then not only dimensions, testing conditions, the velocity of the fluid, they have same pi term as my prototype and model, and then same thing with the drag force. So here, whatever the number I will get, whatever the ratio is going to, that ratio is dimensionless, it does not have a dimension. That ratio for a big plate will be same for my model for my small plate. And I can use this relationship to calculate my drag force, to calculate my resting velocity, and to get my dimensions. So now to test it, what I am going to do, first I am going to get my small plate with the dimensions. So I can find out my dimensions. Once I have dimensions, I am going to calculate my velocity inside fluid. So at what velocity should I test my plate? Because in the air it has a different velocity. When I test it at smaller, the velocity has to be different. So I am going to test my velocity by using this formula, and once I test, I get my results from the model. I get dm. I need to predict what is the drag force on the big thing. That's what I'm going to do using this equation. So drag force, put this one, and then you should get your answer. That's how this thing works. That's how these pi terms work. The importance of Buckingham pi theorem is that whatever the pi term you will get, it will be same for the prototype, same for the model, and you can use that relationship, you can use that similarity to predict how your prototype will behave. That's the whole idea. Let's do a problem and try to understand how does it work. Now in this problem, what we have is a long structural component of a bridge. There is an elliptical cross section of there is some component of a bridge which will look something like this, and it is known that when steady wind blows past the type, bluff the body. So whenever, let's say this is a small component of a bridge, and bridge has hundreds, thousands of these kind of components, and when the wind flows through this component, there are small vortices are formed, this one, this one, this one, and then these vortices at certain frequency could hurt the bridge, could hurt this component. They could cause instability in the bridge. So it could create harmful forces acting on a structure. It is important to determine the shedding frequency. So they will have some frequency, and we want to know what is that shedding frequency is. But we don't have time or money to do actual experiment. We don't have time and money to build actual bridge and find out that frequency on the bridge. So what we do is that we build a small component, a small model of this component, and we test it in water tunnel. That's what it says, to be tested in water tunnel. So here, this is, let's see if it plays. So if you look at it inside water tunnel, if you are testing it, it will look something like this, and you can see this shedding frequency here. You can see this vortices here. So what's happening here is that we have to test this component in the water. So this one is standard air. So this one I have air here, and this one is water. So actual thing will be in the air. Testing is done in the water. So it says that the velocity is 50 km per hour, original velocity. So this air is going to be 50 km per hour. I don't know if you can see that. So this one is 50 km per hour, and the standard air can be assumed, and the diameter is given. So the model dm, model diameter is 20. So this part for the model is given, it's 20. We want to find out what will be the dimension. So here, determine the model dimension. What should be the dimension for the model? Then determine the velocity. Air velocity is 50 km per hour. What should be the velocity for the water? We have to calculate. Then if the shedding frequency is 49.9 hertz, so you do the experiment and then you will get frequencies 49.9 hertz. Then you have to find out what is the corresponding frequency for the prototype. It means you have to predict how prototype will behave from the model data. That's the whole game here. You have to predict how the prototype will behave, how this full size prototype will behave from the model data. And for that we are going to use our pi term. So Buckingham pi theorem, you start with step 1. Frequencies depend on these, list all the variables, these variables we have. You start with step 1 and then you end up with step 8. Step 8 says that this one, W by D by H by D by H, this is your pi 1, this is your pi 2 and this is your pi 3. So this pi 1, pi 2, pi 3 you get, and now your job is to calculate what is the frequency for prototype. The way you have to do this problem is that first you have to find out dimensions by using this one. Once you have dimensions, you have to find out velocity, testing velocity by using this one. And then finally you have to find out frequency by using this relationship. And that's the idea in here. The air at standard conditions is given, viscosity and velocity is given already here. You can use this number and find out the relationship. So now the way we solve this problem is, first we get model dimensions. Now model dimensions is, the ratio is going to stay same. So this is one of my pi terms, dm by hm, m for model is equal to d by h. We have already some dimensions here. Now in the problem they have already given for this model prototype, we have d is equal to 0.1, h is equal to 0.3, it is already given. So this h is equal to 0.3 meters and then d is equal to 0.1 meter. So that is already given. So I'm going to use that relationship, this part d by h, to get the dimensions for this one, and dm, the value for dm is 22 centimeters already given. So now we can use that and to calculate model dimensions, and then here model dimensions I'll get around 60 millimeters or 0.06 meter. That's 60 millimeter or 6 centimeter, 0.06 meters. Once you have dimensions, you can build your model and you can start testing it. So now to test it, you need velocity. Of course, air velocity and water velocity is going to be different because they have different viscosities and then you are testing at different scale. To test it, we are going to use this another pi term. This pi term, here the ratio for model and ratio for your prototype is going to stay same. Our objective is to calculate velocity. We have already velocity 50 km per hour. It is in kilometer per hour. You have to do it. You have to convert it into meter per second. So as for that, first you convert your velocity into meter per second. Means that's air velocity. Air is flowing through a prototype 13.9 meter per second. You use that air velocity here, and then you can calculate Vm. That's the velocity for the model. 4.79 meter per second. That's the answer you get. It means you have a dimensions, you're going to put inside water tunnel, and now you're going to run your experiment with this velocity. Water velocity 4.79 meter per second. You're done. Now, next part. Your objective is to calculate frequency, a shedding frequency, corresponding frequency. Here, as soon as you start doing your experiment with this velocity in your water tunnel, you will get the number for this one, which is given, which is around 49.9 hertz. So you put that 49.9 hertz and you should be able to calculate your frequency. So there is your frequency. You do your calculation, you use this relationship to calculate frequency, and then you will get your final frequency as 29 hertz. So that's the answer that you are looking for. This is a solved problem from the book. You can take a look at it in the book. If you still don't understand, or email me or set an appointment with me and I'll explain it one more time in the appointment. So this is how it works. The importance is that we have this pi term. I think this one is pi 2, this one is pi 3, and this one is pi 1. These are the pi terms that you get based on your Buckingham pi analysis, and these pi terms are the same for the model and same for the prototype, and you can use this relationship to predict how your prototype will behave. First, of course, you need to get dimensions right, then you will get testing conditions right, and whatever the results testing conditions you get, you have to convert them into prototype results with this equation, with this pi 1 term, and that's what you do here. That's the objective. That's how I will say that prediction of a prototype. That's how I can predict my prototype will behave with 29 Hertz frequency from model data. So I did not do a real experiment. I did do experiment inside a water tunnel, and I can still predict what the original thing, how original thing will behave like this, and that's the importance of these analysis, dimensional analysis, or Buckingham pi theorem altogether. Let's do another example. In this example, what I have is a model prototype, is a pump. In this pump is a small pump. I have another big pump. This one is size 1, this one is size 8. Now, one is to 8, that's a difference. The efficiency is 0.88. For efficiency for these both pump is going to stay same, so it has same efficiency as like this one. This one delivers 0.12 mA cubic meter cube per second at height 30 meters. So here the height is 30 meters, and then here the height is 50 meters. So that's the height I have here, 50 meters. I have height 30 meters here. What I want to do, this one, the smaller one, is rotating with 3000 RPM. In this problem, what I have to do is that use that dimensional analysis or similarity requirements to calculate or to predict how this big thing will behave. What will the speed and what will be the flow rate. So data for small thing is given. This small thing is identical to the big motor, big pump. From the small thing, small pump, predict how the big pump will behave, and that's the whole problem. From small one, try to understand how the big pump will behave. Okay. So you do your dimensional analysis and you will get this pi 1 and pi 2. This pi 1 and pi 2 will be exactly same for the model and for the prototype. Whatever the number you will get, this one will be the same for the model prototype. For this one, you will be same for the model and prototype. And in the end, you have to calculate power. Once you have flow rate for this big one, you have to calculate power required for the prototype. So here, this is the formula that I am going to use to get power. So let's use this term to calculate first speed. So you calculate speed. Once you calculate speed, you calculate flow rate. And once you calculate flow rate, you can calculate power. So for the first part, as this term, pi term is same, my speed for prototype, I can use this equation and then I can calculate my speed for prototype, which will get around 484 RPM. So the speed for this one is 484 RPM. This one is 3000, this one is 484. And then finally, I can calculate this flow rate. What is the flow rate for this big thing? So I can use this equation there, and then I should be able to calculate flow rate, which will come around 9.9 meter cube per second. So that's how I can calculate my flow rate. Use pi term, pi 1, pi 2, calculate flow rate. Once you're done with flow rate, you can calculate power required. So here, power required is simply depend on the flow rate. The rest of the data is given. You can use that data and you can calculate power required, which is around 5.5 megawatt. This is very simple example. All you have to do is understand the formula, put the numbers in and get your results. But make sure that you understand what you are doing. You are simply doing, you have a data for small model pump, you are using the data to predict how this big pump will behave, and that's the whole idea of dimensional analysis. There is a video, you can look at the video later in the PowerPoint. Now, final part for this chapter, some common dimensionless group in fluid mechanics. When you do these experiments, there will be always some numbers that they will repeat themselves. So one of those numbers, it means that some dimensionless parameters, they will repeat themselves. So like this one, rho v d by mu, density, velocity, diameter by viscosity. This is something known as Reynolds number, and it will repeat itself, and we will learn more about Reynolds number later in chapter 8. For now, you need to just see that as you do experiments, these experiments, some parameters they repeat, so we already have some definitions and some idea about them. So, Reynolds number was given by the guy named Oswald Reynolds, and it is given as rho v d by mu. We'll learn more about it later in chapter 8. So that's one of the most common dimensionless parameter. If you're doing experimentation with any fluid, this number will repeat at velocity, at some viscosity. This is very common. Then there are a few other numbers. But before that, let's do one problem. Here in this problem, this is a problem for Reynolds number. In this problem, we have a blimp, something like this, a blimp which has 60 meter long and 5 meter wide. It's going to be studied in a wind tunnel. You are going to study this thing in the wind tunnel. The model is 1 to 10 scale. So you have, this thing is very big. You have to test this thing in wind tunnel. So it's going to be very small and then 10 times smaller than actual size. So whatever the big thing, this small thing is 10 times smaller. The prototype will fly at 10 meters per second. So here for this one, height is, the velocity for air is 10 meters per second. What we want to do is that find out what wind speed should be used in wind tunnel. So if you are going to use this thing in wind tunnel, what should be the velocity? That's what the idea is, that both where we have air. So here we have air, in the wind tunnel we have also air. So for that we are going to use this relationship, Reynolds number. Reynolds number is a dimensionless term. It's going to be same for this big thing, for this small thing. So I'm going to use this formula. Now here, as it is air, density same, viscosity same. Now I have only thing that is remaining is Vv, velocity I have to calculate. Velocity is given, diameter is given, Vm I have to calculate this one. So here, this one velocity is 10, the size 1 is to 10, so that big thing size is 10. Here size is 1, I want to calculate this thing. So as you can see, this one is 1, this one is cancelled. So 10 into 10 is 100 meters per second. So your final answer should come as 100 meters per second. So that's the number that you will get. Ultimate, what the wind speed should be used in wind tunnel, and that will be 100 meters per second. That's the answer that you're looking for. So you can use this Reynolds number to solve this kind of problem. Now, some other common dimensionless parameters. Froude number, if you are dealing with open channel flow, if you are dealing with ship design, Froude number will play its role. Froude number is simply velocity of the fluid divided by under root gravity into length or gravity into depth of the fluid altogether. So that's your Froude number given by the guy named William Froude. Euler number given based on the name Swiss mathematician Leonhard Euler. It depends on the problems with pressure. If you are dealing with very high pressure difference, Euler number will play its important role. That's one more dimensionless parameter. Another one is Cauchy number. If you are dealing with compressibility of a fluid, bulk modulus, Cauchy number will play its role. Then Mach number, one of the famous number, Mach number based on the guy named Ernest Mach. Mach number is nothing but object sound divided by speed of sound. So if you are below speed of sound, you are subsonic. If you are exactly of speed of sound, you are transonic. If you are more than speed of sound, you are supersonic. And then if you are 5 times more than speed of sound, you are hypersonic. So that's the Mach number. If you are dealing with very high velocities, then in that case you have to deal with Mach number. Mach number will be one of your pi term. And then finally we have some other numbers, Strahl number and Weber number. Strahl number is when you deal with something with frequency, something with oscillations. If you're dealing with that, some oscillations, experiment involves oscillations, Strahl number is mostly you're going to deal with. You have to, it will repeat, and then Strahl number for your model, for your prototype will be same. And Weber number is same thing. If you're dealing with an experiment which has surface tensions important, surface tension is important, in that case Weber number for your model and for your prototype will be same. So these are some common dimensional groups that will repeat themselves as you do your experiments, and that's the final part for chapter 7. So now we are going to stop today for here chapter 7. If you have any questions, just email me or set up an appointment with me, and we'll stop today. We will have our exam at the end of this month on chapter 1, 2, 3 and 7. Again, if you have any questions, feel free to email me. That's all for today. Thank you and stay safe.